Over to you, Victoria.
Great. Can you see my slide, Abby?
Yep.
Great. Well, thank you very much. And I'm just going to spend a little bit of time today providing an overview of the Salinas Valley hydrogeology. So hopefully you've all seen this slide before. This is just covering what a hydrogeologic conceptual model is, and that really is just the foundational understanding of the basin. And everything builds from this in our basins. The image that I have here is of a different basin, but I like this image because it shows that conceptual understanding of what the basin looks like, including the bedrock and where the basin materials and aquifers and aquatards are found. But at the land surface, we also see water budget components built on top of this. So I think this is a great image to convey that everything builds from our understanding of the basin. We build our models off of it. We complete our water budgeting, and everything else just slowly builds on top of what our understanding of the basin is. So how do we build our understanding? Well, we build it with a lot of data. We use a lot of published reports and cross sections. We use geologic maps. We have a lot of well logs. Here in the Salinas Valley Basin, we have an abundance of AEM data. And then we can also use our own observations as trained geologists and hydrologists. And all of these data are available in this basin. In some areas, different types are more, other types are more in other areas, but we bring this all together to build our conceptual understanding of the basin. So we're going to start at the surface and then slowly work our way down. This is the Salinas Valley watershed, outlined in purple here. And the watershed is where all of the rain that falls slowly makes its way to the Salinas River. And all of the water in the valley comes from rainfall. The valley does not import water from outside of the watershed. The water use is both surface water and groundwater. And a note about the deeper groundwater is older, and recharge from the surface can take thousands of years. So depending on how deep you are in the subsurface might indicate just how long that water has been in the subsurface. So speaking of the river, we start in our basin with the reservoirs, which are owned and operated by Water Resource Agency. And the Salinas River is managed for both groundwater recharge and the SRDF. But I want to point out that here the surface water and groundwater are a joined system, since we know that surface water does make it into the ground in certain key locations in the basin. They are a part of one whole water system here. So this is the beginning of our conceptual understanding, the Salinas Valley Basin conceptual understanding shown here on the screen. I want to point out that on the right side of this image here, or towards the south, there's a single basin system. And then as we move to the north, it turns into more of a layered system near the coast. And that's shown here with the sort of reddish colors versus the brown colors. We have our stacked aquatards and aquifers, the 180 foot, 400 foot and deep aquifers. And as I mentioned before, the Salinas River is a very important component of basin water, especially those areas where the aquatards don't separate the river from the basin material. So first, I'm going to touch on a little bit of geology and hydrology. The image shown on the right here is just our surface geology map. If you were hiking through this area, these are the geologic units that you would walk over. But as we get into the subsurface, we encounter different geologic units. And these are the general units that we encounter listed on the left here. Now, this line that I'm showing separates the generally water-bearing units from the generally non-water-bearing units. So below this line, the Monterey Formation, granite, and other crystalline rocks, these are rock units that generally don't make water. So we consider them basement or bedrock units. And then all of the units that are above this line are generally water bearing, where a lot of production wells are situated, and they make water sometimes better, sometimes less good than others, but this is generally where we find our water. And that water is found in what we call the hydrostratigraphy. So the geology and the hydrostratigraphy, they're not exactly the same, but the geology supports where we find our aquifers and aquatards. And this is kind of those cross relationships that we see between shallow sediments, the 180-foot aquifer, the 400-foot aquifer, and the deep aquifers, or in other locations in the basin, what we would call just basin fill aquifer, if there are no aquatards that separate them in the subsurface. Here I'm going to touch on sort of the shape of the basin. Now, the image on the right seems maybe not so easy to understand. We have these blue areas, we have these red areas, but really what this image is conveying is the overall shape of what we see in the Salinas Basin. So starting from the left with this image, sort of towards the middle of the whole basin here, we have this deep sediment-filled basin. The bedrock is much deeper, and there's a lot of space to hold a lot of material. As we move further south, that bedrock rises up and the basin gets a lot shallower. And this is just sort of the bathtub shape, the shape of our bathtub in effect. And when we cut across the basin here, between these two mountain ranges, the Sierra de Salinas and the Gavilan Range, we sort of have this tilted V shape. Again, this is just to show you the general shapes of what the basin looks like, how these sediments have filled in and where our water occurs above the bedrock. So just keep that in mind as we go through some of the slides as we move forward. The first thing I want you to keep in mind is that generally the water-bearing sediments in the Salinas Basin are hydraulically connected, right? Unless we have some silts and clays, and that reduces connection. But if the sediments are in contact with one another, they're probably going to be connected. Groundwater flows horizontally more easily than it does vertically. And this image here, if you can see the red lines in these blocks, you can see that those red lines are showing an easier path horizontally than vertically. And that really mirrors the horizontal layering that we see as sediments get deposited over time. And then the other thing I want to point out is that groundwater moves slowly. Definitely more slowly than water flows in the river. Certain areas, groundwater will move faster or groundwater will move slower than other areas. So if you have an area with a lot of sand and gravel, you can expect your groundwater to move a bit faster than in an area that has a lot more clay and silt. But on the whole, groundwater moves pretty slowly, especially compared to the river water. And then a note here about the deep aquifers. These are the results from the deep aquifers study. The deep aquifers are present in more of the basin than previously conceptualized, and this is based on a continuous separating aquitard encountered in the subsurface. Where this aquitard is found, we find the deep aquifers extend into the forebay, eastside Langley, and seaside subbasins, as well as offshore areas. So the areas on the map here that are solid yellow, this is our known and confident deep aquifers extent. And you're going to notice on this map that there are these yellow hatched areas. These are areas where we do have data to indicate that the deep aquifers are present, but just not enough data to really definitively draw that line out there. But there are data to suggest that they do extend even a little bit further. Now, one final note about the deep aquifers before I move on is that there is no known direct surficial recharge relationship. All of the water that has been collected and sampled and age dated has not indicated that any of the water in this aquifer system is young or related to surficial recharge. And that's what we know about the deep aquifers so far. So now I'm going to get into subbasin by subbasin cross sections and kind of go into a little bit more details as we go through the basin here. But before I get into each subbasin, I want to orient you to some of the things you're going to see on each slide. I want to point out first and foremost that the cross sections I'm going to show depict groundwater flow model layers, which are these hydrostratigraphic layers, or just the aquifers and aquatards. And when you look at the colors, just think that the warmer colors, like the oranges and the yellows, those are our aquifers, and sort of the cooler colors, like the blues and the brownish grays, those are more of our aquitard layers, or places where it's a lot harder for groundwater to flow. Each cross section is going to have a map and a line across that map that shows you where the cross section is oriented in the subbasin. All of the cross sections should show you which layer we are looking at. And you're going to notice that some of these explanations are showing either a common name, or what we have here, say in the middle, is like the 180-foot aquifer or equivalent. And that's where we're trying to really show that these layers might be known as one name in one subbasin, or might be known as another name in another subbasin, but really they're the same sediments or the same layer that we find cutting across more of the basin. Finally, you're going to see a lot of the wells that we use to help build these cross sections with this borehole lithology. It is a simplified lithology. We have clays in brown, bedrock in black, and this white color, we just call it not clay, but just think of that as sand and gravel. We also have a hard pan notation, and I will point that out in the subbasin where that's more prevalent. And then you'll also see these blue arrows on the cross sections. And these are arrows that show our general understanding of the direction of groundwater flow on that cross section. So all of this is to say, when you start seeing the cross sections in the next slide, these are images that show our best understanding of groundwater flow paths, groundwater flow obstructions, and our understanding of what's going on in the subsurface. So let's get into it. So starting with the Monterey Subbasin, the Monterey Subbasin is situated between the Seaside Subbasin and the 180-400-foot aquifer subbasin. And the Monterey Subbasin has these two management areas shown in the map on the bottom right of your screen there, sort of the blue purple color and then the orange color. And these are not separate, these are different management areas, but we also find that they are different hydraulic areas. This really is a divided hydraulic system. So the Marina Ord area, which is more of that blue color and shown on the cross section here, this is a hydraulic system that more closely resembles the 180-400 subbasin. We have our stacked aquifer and aquitard system. There are minor differences that we find in the Monterey subbasin, but you can pretty much see how that relationship cuts across here. As we move to the right of this cross section, this is the Corral de Tierra management area. And this is an area that has encountered a lot of geologic structural deformation and has become hydraulically isolated. And you see over that bedrock rise, there's a cluster of wells on one side, this great space in between, and a cluster of wells on the left side, really denoting the two areas of groundwater production in this area. And we generally would expect to see the groundwater flowing in these directions here, right, towards the areas of more pumping between these two areas, but not much relationship between the two. This next cross section, also for the Corral de Tierra area, this goes down Toro Creek. And again, we see this isolated area on the left. And then as we move over, again, a bedrock rise moving towards the 180-400 subbasin, it starts to then again resemble that stacked aquifer and aquitard system in the 180-400 subbasin. And again, these are those expected groundwater flow directions going towards the areas where we see a few more wells, but definitely separated by that bedrock rise. Moving to the 180-400 subbasin, this is that coastal stacked aquifer system many folks are familiar with. This system is very well connected to the Monterey, Langley, Eastside, and Forebay subbasins. And this is generally the direction of groundwater flow in the subsurface. This is a cross section that goes down the axis of the valley here. But these next two cross sections, these cut across the 180-400 subbasin. B to B prime on the left is a bit of an oblique angle, and then C to C prime here on the right, that really cuts across the basin. You're going to notice on both of these cross sections that there is a black dashed line vertically that shows the subbasin boundary between the 180-400 and the east side subbasins. So really what I'm showing in these cross sections is the continuity of these sediments beyond those jurisdictional boundaries and how it's really all related. The other thing you're going to notice in these cross sections are these little black dashed lines on the right of each cross section. And these are areas of alluvial fan deposition coming off of the Gavilan Range. And that's really to say, along the Gavilan Range, when there are storm events or rains and we see floods and flash floods that come out of the smaller canyons, a lot of times that material is very mixed with sand and silt and other sediment, and that washes out down from the mountain and then gets deposited in these big fan-like shapes. And we see how this comes out in the subsurface, and this comes out in the subsurface as being more clay rich. So even though we've drawn here in the cross sections that the layers go across, the area with the black dashed lines is really to show an area where we encounter a lot more clay because of this alluvial fan deposition. And so the hydraulic connection or the hydraulic behavior in the subsurface is going to be a little bit different here. And these are those groundwater flow directions that we expect to see along these cross sections. The one on the right, the groundwater flow direction is away from the screen, and that's just really hard to show with an arrow. So I label it like that. Moving to the Langley subbasin, this is a very unique subbasin because it has very uneven aquifer properties, which leads to a lot of perched water. So this is an area where if you look at those wells that are along this cross section here, you're going to see that gray symbol denoting hard pan. So the aroma sand, which really dominates the Langley subbasin, has these hard cemented areas within the formation that perch water. And so the groundwater levels throughout the Langley subbasin are very difficult to relate to one another. And so we wanted to really denote that in this cross section. The other thing we find in the Langley subbasin is that there are a lot of small domestic bedrock wells. So that is the gray with the black hatched lines there on the left. There are these small domestic wells that have drilled into fractures in the bedrock, the granite that we find out here. And these fractures can convey some water, but it's really not much more than what a household can use, and sometimes not even as much as a household can use. So not a very reliable system there, and not making a lot of water. This is, for this cross section, the direction of groundwater flow we would expect if we didn't have so much perched water, and we're still figuring that out. This cross section goes across the Langley subbasin, and again, this is the general direction of groundwater flow we would expect sort of from the higher areas to the lower areas. But again, you can see as we move down the Langley subbasin, we slowly start to build into our expected layered aquifer system when we encounter the 180-400 subbasin there on the left side of the cross section. Now we've gone into the east side subbasin, and hopefully you recognize this cross section from a couple slides ago. This is the one that cuts across both the 180-400 and the east side subbasin. And again, that subbasin boundary is marked with the black dashed line. And what I have on this slide is I have both the cross section that we have developed, but I also have an AEM transect shown here. And this is really to show you how we have determined the extents of those alluvial fans in the subsurface and what it looks like in the data, how we relate what we see in the data, this big blue blob on the AEM transect kind of outlined in a dashed color here. and then what it looks like in our cross sections with those black dashed lines. And you can see that the alluvial fan extents where we have a lot of clay in the subsurface mixed in with all the sands and gravels. These are much larger and far more extensive than we had previously understood. And it does impact the way that groundwater can flow. Now, this next slide here for the East Side Subbasin, this is really to illustrate the next 2 points about the East Side Subbasin. Because it is this mix of alluvial fan material, and there are multiple alluvial fans that meet and overlap one another over geologic time, it's very difficult to confirm any sediments or layers across distances. So I have the cross-section that was included in the GSP on the bottom right, and this shows the wells and the different lithology descriptions that were made to help construct this cross-section, and you can see how discontinuous it is in the subsurface. Even though the cross-section on the top of the screen shows these nice continuous layers, again, this is just to show how we do our best to understand the subsurface and build out groundwater flow model layers. But really think of the East Side Subbasin as having a lot of discontinuous lenses of sands and clays, being more clay rich than a lot of the rest of the basin. And then the other thing to keep in mind with the East Side Subbasin is that it has shallower bedrock than was expected. And that has an impact also on how groundwater flows. And this is our expected direction of groundwater flow along this long axis of the East Side Subbasin, generally. Now, as we move south into the Forebay Subbasin, again, this is another subbasin that is dominated by alluvial fans, but it's different on each side of the subbasin. Along the Gavilan Range side of the subbasin, we still have those clay-rich alluvial fans that have built up over time. But on the west side of the subbasin, there's the Arroyo Seco cone. And this alluvial fan, it is very gravel and sand rich. So it's very conductive. It conveys a lot of water. And it's also very, very large and has built up over time. And it's so large and has built up so much. If you look at the map, hopefully you can see it, but if you look at other maps, you'll definitely see it, that it has pushed the Salinas River to the other side of the subbasin. The Salinas River hugs that eastern boundary closer to the Gavilan Range because of the influence of the Arroyo Seco cone. And again, this is a very familiar cross section, and I say familiar because it looks a lot like the one that crossed the 180, 400 and the East Side Subbasin, but this just cuts across the basin here. And again, it shows that tilted V shape with the bedrock. This is a neat one because it shows two large alluvial fan developments over time. But again, similar patterns we see north of here as well. But just to really convey the influence of how the alluvial fans have built up along the front of the Gavilan Range there. So as we move south, our final subbasin is the Upper Valley Subbasin. This is where the bedrock gets a lot shallower. And here in the Upper Valley Subbasin, the bedrock is a combination of the Monterey Formation, the granite, as well as the Pancho Rico Formation. So the Pancho Rico Formation is a geologic unit that has very low permeability. And if there is water encountered in the Pancho Rico Formation, it typically has a high salt content. It's very salty water if we encounter it here. So it is not used for any production. And because of its low permeability, we group it together with our broader bedrock understanding. The majority of the wells in the Upper Valley Subbasin are in the high conductivity, shallow river-connected sediments. And if you look at the cross-section and you look at the wells that are placed along the cross-section, you'll see they're not very deep. Most of them are in that shallow river-connected sediment there because, again, the bedrock is shallow. And so where else are you going to drill? You want to make water in your wells. So because it's so shallow, you'll also notice that these cross sections are very vertically exaggerated. This is the general direction of groundwater flow. And if we move to these other cross sections that cut across the Upper Valley Subbasin, B to B prime here on the left, this is closer to King City. And again, a lot of those wells are really shallow and kind of clustered closer to where the higher conductivity sediments are. And the cross section on the right, C to C prime, this is in an area of the subbasin with expanded boundaries from sigma. And so because these boundaries were expanded, it encompasses more geology than previously. And you'll notice that there's a darker orange unit here. This is an unnamed sandstone. Now, we don't have any wells that are drilled into the sandstone. We group it together with the Paso Robles Formation for groundwater modeling purposes. But it was just sort of an interesting thing as we were going through the data to see this separate unit, but be able to include it for potential future management, if any at all. But this is one of the results of that expanded boundary and understanding this broader area of subsurface. And this is the expected direction of groundwater flow. And this is all of it put together along the basin axis. So these are the three of the cross sections you've seen before for the 180, 400, forebay, and upper valley subbasins. You can see that basin geometry pretty well in the gray unit at the bottom of each of these sections, and the way that these layers really are connected. And again, groundwater flows from south to north, just as the Salinas River flows from the south to the north. And just to point that out again, this is an image that shows the groundwater contours from south to north in the 180 or equivalent sediments. And again, just showing the direction of that groundwater flow through the whole basin. So I'm just going to leave you with a few key takeaways here and then pause. The Salinas River is important for groundwater recharge, and the reservoirs are owned and operated by Water Resource Agency for groundwater recharge and diversion at the SRDF. The groundwater basin is hydraulically connected, but to varying degrees, depending on where we find concentrations of clay in the subsurface. Aquatards, or clay layers, inhibit surficial recharge where they are in the basin, and this makes certain projects and management actions more challenging. The conceptual views that I've presented here are scaled for the valley and not individual projects. So if you have individual project sites, those are probably going to require a bit more investigation to really understand what's at the subsurface right there. But with what we have right now, we have a pretty good understanding of the basin to move forward with various ideas and projects and management actions. And so with that, I am going to pause and take any questions that you might have.
Well, Victoria,